So, hello everyone. Well, first of all, I would like to thank the organizers for accepting my talk in this wonderful workshop. In this talk, I will try to argue that certain class of free quantum fields in cosmology, in sharp contrast to classical test particles, that they can be well defined as distributions in even if we enlarge the spacetime to include the curvature singularity. So this is work done with different researchers here. Okay, I'll try to summarize the results from 3 different papers in which different researchers have contributed: Abay Astecar, Tommaso De Lorenzo, and Mark Snyder, and myself. And yeah, so let's get started. So as you know, singularity theorems in general relativity are often interpreted to mean that the cosmological Big Bang is an absolute barrier beyond which physical theories cannot be extended. Okay, indeed, we all have in mind the fact that when probed with classical test particles, the past evolution of timelike geodesics is not well defined after a finite proper time. So one generally expects quantum gravity to remedy this situation. Indeed, there are some explicit realizations of this idea in loop quantum cosmology, where the classical Big Bang singularity is replaced by a smooth spacetime bounce, and in which, in principle, one could probe the Big Bang with classical test particles by traveling back in time across the Big Bang and exploring the spacetime beyond. Although this is expected, the thing is that classical test particles are actually an idealization. And so to really probe the spacetime structure around the curvature singularity, we really need better descriptions of matter, like quantum mechanics. It may happen that because singularity theorems only concern geodesic incompleteness, it may happen that other descriptions of particles or of matter may be better tools for describing the Big Bang. In other words, that the spacetime doesn't appear as singular when probed with better tools, better probes. So this idea was somewhat formulated and explored in the past by Horowitz and Marov for the first time. They studied the evolution of quantum test particles instead of classical test particles, and they concluded, well, on certain static diatonic black holes, which include some timelike curvature singularities, and they concluded that the dynamics of the wave functions of these quantum test particles remain well defined in a precise mathematical sense, despite the presence of this curvature singularity. Now, unfortunately, quantum test particles, well, for more interesting physical settings like cosmology, the dynamics of the spacetime will lead to the phenomenon of particle creation, and so quantum test particles are no longer suitable as probes. The only adequate description that remains is quantum field theory. So in our work, and this is what I will try to summarize in this talk, we studied a certain family of quantum scalar fields and physical observables constructed from it, and we concluded that they can be formulated as well-defined distributions in a considerably wide family of cosmological spacetimes, even when the spacetime itself is enlarged to include the Big Bang curvature singularity. So basically, in a nutshell, the idea is that as an operator value distribution, the potential divergences that this quantity may have will be compensated by the spacetime measure. So integrals are actually well defined, even if we integrate over the full real line. Okay? So to arrive at this conclusion, we worked in the framework of algebraic quantization of fields. In the usual approach, this framework is based on a 2-step procedure. One first specifies a suitable star algebra, which is meant to represent the observables, the physical observables of your theory. And then in a second step, one specifies a state which allows you, via the GNS construction, to recover the usual Hilbert space description of states in quantum theory, and in which elements of this algebra are represented as linear operators, satisfying fundamental algebraic constraints such as the canonical commutation relations. So the thing is that the field algebra can be the first step in this construction. The field algebra can be specified already using the structures available in the classical phase space, in the classical theory, in particular from the phase space. Ordinarily, one focuses on smooth solutions with compact Cauchy data of the field equations, and then for globally hyperbolic spacetime, the Klein-Gordon operator admits well-defined Green's functions, and so elements of this phase space can be basically labeled by smooth test functions. And similarly with the symplectic product. At the end of the day, the classical phase space can be entirely specified by smooth test functions and the causal propagator. So the idea then is to construct the a free star algebra generated by all these symbols that are labeled by smooth test functions, subject to some physically motivated algebraic constraints that you eventually want to be satisfied in a Hilbert space. Elements of this abstract elements of this algebra are then represented in terms of linear operators satisfying the same algebraic constraints on a Hilbert space when a choice of state is given. Now, while this usual formulation of algebraic quantization is extremely useful in quantum theory, to account for the infinitely many unitary, infinitely many Fock representations in quantum theory, the thing is that for the problem at hand, unfortunately, it will not be sufficient because we will work this extended singular cosmological spacetime that I'm talking about will not be globally hyperbolic, and furthermore, the solutions of the field equations will not be smooth. They will be singular in some sense. So before addressing the problem that we want to address, we need to slightly reformulate it to accommodate our problem. So the idea is basically the same. The field algebra can be specified already with the structure available at the classical level. But now, instead of focusing only on smooth solutions of the field equations, we will enlarge the phase space and admit elements that satisfy the field equations only in a weak sense, in a distributional sense. Okay. Then the idea is to construct similarly a free star algebra generated by now these symbols, but instead of being labeled by smooth test functions, now we don't have causal propagators a priori, and so we cannot use the same trick as before. We label the elements of the algebra by elements of the phase space directly, okay, which are distributional and subject again to physical fundamental properties that we want to be satisfied in the Fock space or in the Hilbert space representation. Okay. The thing is that if you restrict the phase space, the elements here, to smooth solutions in the field equations, these two algebras are essentially star isomorphic, and the resulting quantum theories are completely equivalent. But this slight reformulation is a bit more general, and it will be particularly useful in extending quantum theory beyond the Big Bang singularity. So the idea now is to apply this framework, this slight reformulation of algebraic quantization to specific problems in cosmology. For the models of interest, I'm just restricting to the usual Friedmann-Lemaitre-Robertson-Walker metric in spherical coordinates, and we'll do the analysis for any spatial curvature. The Big Bang occurs when the scale factor vanishes, and one can always choose a suitable time coordinate eta, such that this happens for that the Big Bang is located at eta equals 0. And what we do first is to analyze the problem as usual for the globally hyperbolic part of the spacetime after the Big Bang, and then I will discuss how to extend it back in time to get a well-formulated theory, quantum theory in the full extended cosmological space. Okay. So to obtain the phase space, we need to look for the solutions of the equations. As usual, we take advantage of the symmetries of the background, and we look for separable solutions of this form. Okay, when you plug this on the Klein-Gordon equation that for simplicity, for definiteness, we focus on the massless minimally coupled case. Then the Klein-Gordon equation separates in two parts. The first part is just an eigenvalue problem, which can be solved in full closed form, including useful identities for completeness and orthonormal relationships. And then the second equation governs, once a scale factor is given, it governs the time evolution of the field modes. Okay? Since we are interested in the Big Bang, in the curvature singularity, well, physically interesting cosmologies with a Big Bang include radiation and dust universes, and we studied these ideas on these backgrounds. Okay? So, in any case, in all cases considered, this equation admits analytical solutions, and we are allowed to construct the phase space simply by taking suitable linear combination of a given basis solutions of this equation. Okay, the coefficients in these linear combinations, z of k, they serve to label uniquely each element of our phase space. So then the idea is now we are given this classical phase space is just to reproduce the idea that I described in the previous slide. We can construct the star algebra A of capital F, where I recall that the generators of this algebra are just symbols labeled by elements of this phase space. In the previous case, in the previous slide, because I'm restricted to the smooth part of the manifold, this is so far a smooth solution. So for the moment, there is nothing new. In order to find a Fock representations of elements of this algebra, okay, we decompose between positive and negative frequency solutions. This allows to introduce a complex structure in your phase space, which in turn can be used to define a canonical Hermitian inner product in your phase space, which in turn allows you to define a Gaussian or quasi-free state in the algebra, which via genus construction recovers your Fock space. And in this Fock space, elements of the algebra are mapped to operator fields, which can be expressed as smear out integrals of these operator value distributions. Now suppose a key point in this expansion here is that typically the time-dependent part of these field modes typically diverges at the singularity. Oops. Okay, well, the field modes typically diverge at the singularity. So if one wants to extend the spacetime beyond the Big Bang by allowing the time coordinate eta to take values on the field real line, then if one identifies these elements, these field modes as functions, they will be ill-defined. However, in quantum theory, it should be noted that the field modes are actually operator value distributions. And in fact, in all cases considered, these field modes, we notice that they only diverge polynomically. It is well known from the theory of distributions that inverse polynomials can be well defined as distributions on the full real line. So we take advantage of this to define a phase space as before, where elements F of this phase space satisfy the Klein-Gordon equation only in a weak or distributional sense. Okay? Furthermore, because the symplectic product is constant on each space-like hypersurface, we can extend it by continuity to negative values of eta, and so the canonical commutations relations in the algebra are still well-defined even if we extend the spacetime across the singularity, simply by continuity of the symplectic product. In summary, without entering into technical details, the problem is such that we are still allowed to quantize the theory with this star algebra A of capital F generated by these symbols, because they satisfy the canonical commutations relations, even if the spacetime is enlarged to include this curvature singularity. And the elements F are well defined as distributions. This is the algebra. To get a Fock representation is basically the same story. F defines one particle states, and while they might be divergent at the singularity, their norm is well defined, and in fact, the inner product is well defined for any pair of solutions F1 and F2. This allows, again, to introduce the Gaussian state Gaussian state as before. And in turn, this leads us to a folk representation of the algebra, in which now the operator value distribution, phi of x, is written in a basis of mode which are distributions. Okay? Classically, distributions are not physically relevant, but in quantum theory, the field modes are allowed to be distributions. And so I'm just finishing. I think I don't have much time to get into the details, right? So these are just explicit results, nonlinear observables. The field modes are given on the slide. Oops. Apart from the field operator, one can also check that physical observables constructed from it also remain well-defined as distributions on the full extended spacetime. We check that using Hallmark normalization for both spatially closed and open universes, and for radiation and dust field universes. And well, since I don't have much time, I'll leave it 1 minute. Okay. So basically, the conclusion is that we were using the fact that in quantum field theory, we are allowed to take advantage of distributions. Actually, we can probe the Big Bang with quantum fields, and we see that the spacetime doesn't appear as singular as it happens for classical particles. Nonlinear observables, such as the vacuum polarization or the stressing tensor, are smooth away from the singularity, but they can still be regarded as well-defined distributions on the full extended spacetime. We are currently working with a similar problem with the Schwarzschild curvature singularity, and so far we are obtaining more or less similar conclusions. And just a final remark, this work can be thought of as well. The observations made here may hint some faithful shadows of a full theory of quantum gravity, as for instance in quantum cosmology, where it is expected that at the Planck, in the Planck regime, there is some hints that geometries may be distributional. So if you plug this stress energy tensor on the semi-class analysis equations, you would recover more or less this. So one can think of this as some sort of semi-classical limit. And I'm done with this. Thank you for your attention.
Okay, so quick question, please, because we are a bit late on the schedule.
Sorry, a very quick question then. So you went a bit fast through the previous slide, but do I understand correctly that the state, the quantum state, if you continue it through the singularity, then at -8 will also be Hadamard? Or
yeah, you can check that there is Hadamard at both separate parts, and we check that if you split the points, we simply check that this is Hadamard by brute force. Okay, we separate and using symmetries, and so we obtain the. In this case, I didn't show it because it's very nasty expression, but we check that there is Hadamard at both parts of the singularity, and we also check that if you split the points and you put one point in one side and on the other side of the singularity, it is still Hadamard. Okay,
so do you also know if there's some kind of wavefront set based argument? Or?
No, we don't have that. No, we haven't analyzed it. That would be a better, a more elegant way to prove it.